Explicitly programming with MetaHaskell by Geoffrey Mainland.
Okay, is this on? Okay, there we go. Okay, I'm going to start by telling you a story of an unfortunate functional programmer. And that would be me, of course. So why was I unfortunate? Well, it turns out that I sat in graduate school in a lab with a bunch of systems people. That's not why I was unfortunate, but they would have said I'm unfortunate because I'm a functional programmer. I disagree. The reason I was unfortunate was that I didn't get to write in a functional language. Why was this? I was programming embedded systems, essentially. So this is a T-Mode Sky. It's a small 16-bit CPU, 10K of RAM. I was programming a bunch of these, about 200 with wireless radios. Can't really use Haskell. Or can you? Well, the solution is I built a little DSL called Flask that generates code that runs on these devices. So then I could write my programs on Haskell, right? This is a great idea. Of course, it's not a new idea. This is a Vertex 7 FPGA. There's a classic Haskell DSL, Lava, that's meant to program these sorts of devices. Plenty of other examples. NVIDIA, Tesla, GPU card. We actually have 3 Haskell DSLs that I know of for programming these guys. Right? Accelerate, Obsidian, and my own attempts, Nikola. It's another device. This is an Ericsson RBS 6202. This is a base station, a phone base station, GSM base station. Of course, there's a group at Chalmers working on Feldspar, another DSL for programming these devices. I'm going to throw one more guy in here. This is a Net FPGA 10-gig card. You can think of this as a programmable router. So I don't know anyone who's done a DSL for this device yet, but I do know something. So we as a community have really brought the power of Lambda to this domain and dominated it, right? So it's great. It's functional programming. We took these devices and thought, you know, these require this kind of low-level Bronchi code to write, and what have we done? We've taken functional languages and used them to program these devices. I will note that so the way that you bring functional languages to these devices is generally through code generation, through metaprogramming. So you don't program directly in, say, Haskell. You write a high-level program that generates code, then runs on these devices. So these are really metaprograms. So written in Haskell when they generate some C code or some RTL or something else, right? So aside from all this exciting work, meanwhile, there's actually a lot of code produced by these metaprograms, these code generators in the wild. The prototypical example is FFTW. This is the fastest Fourier transform in the West. It won many awards. It's used ubiquitously. And what it does is a camel program that generates specialized FFT functions. Another example is Atlas, automatically tuned linear algebra system. So this will, when you install it, profiles the code in the BLAST library, generates a specialized BLAST library for your platform. And the final example I'll show is Spiral. So this is a specialized code generator for DSP transforms. And it turns out that code generation is all over the place, in the wild, in the real world, especially in high-performance computing. And I want to show you an excerpt from, I'm going to pick on Atlas here. I'll show you an excerpt. But I particularly like this comment here. So if you look here, how are they doing code generation? Well, there's really only one function they're using. There's only one function you need to do code generation. That's fprintf, right? Of course. I think it's appropriate to insert a comment here about glass houses and stones. So surely there's a better way, and I'm going to be a little more charitable than the Atlas developer who wrote this comment, but surely there's a better way to do code generation. Right? I think we need better language support for metaprogramming. So of course in the Haskell world, things are a little bit nicer, right? But I'd still argue even there, we still need better support for metaprogramming. Right? So we have lots of theory in the programming languages community about homogeneous metaprogramming languages. And when I say homogeneous, I mean the language that is manipulating these terms is the same language as the term that it's manipulating. So MetaOCam or MetaML are prototypical examples. And we have a great implementation of the metaprogramming language, MetaOCam. Of course, all these applications I've showed you, or most of them, you really need some heterogeneity, right? So if we're writing Haskell programs that generate a program in C or RTL or something else. So we'd like to be able to have a metaprogramming system that allows us to generate code in multiple languages, I would argue, and we still want some guarantee about the type safety of the code that we're generating, the programs that we're generating. So what's the approach that I'm going to take? So the idea behind MetaHaskell is that we're going to take a single meta language, in particular it's Haskell with some slight modifications, and we're going to allow multiple object languages to be used here. Right? So we're going to make this an explicitly heterogeneous metaprogramming system. We're going to parameterize the meta language type system in some way. I'll tell you how later. I'm being very vague right now. By the object language type system. And we're going to appropriately modify the object language type system to support the kind of things, the operations that we want to do when we're metaprogramming. So for example, when we're constructing these terms, we're splicing terms together, so probably need to modify the object language type system to support that in a type-safe way. We're going to want to work with terms with free variables, so we're going to have to support that somehow. But we still want to guarantee that well-typed metaprograms are going to produce well-typed object programs. And in particular, if we produce a closed object language term, then it's going to be well-typed with respect to the original unmodified type system of our object language. So just to drive things here, I'm going to show you an example of heterogeneous metaprogramming. It's just a first attempt. Okay, so our meta language is going to be Haskell. Our object language is going to be C. It's not going to be type correct. So what I mean by type correct is we're going to generate some code, but it may not pass the C compilers. No, I'm not saying type safe because this is C. Why would you say type safe? So I'll say type correct. Okay. This is something you can do today in GHC. So here's our program. This is a kind of classic example from the metaprogramming literature. It's a specialized power function. It's a little silly, but it's small, fits in the slides, and it serves to illustrate my point. So what we're assuming here is we're going to raise numbers to an exponent, but we know the exponent ahead of time. So we might as well specialize this code to take advantage of that fact. So what do we have here? Well, we're quoting kind of two syntactic categories of C code. We're quoting C functions and C expressions. These two guys are quasi-quoters, and in GHC's implementation, they actually have a type quasi-quoter here on the screen in red. What they are records of functions that take a string and produce abstract syntax. So this is just syntactic sugar. I want to emphasize this. So as a whole, these brackets are quotes. So what you can think of it, kind of operationally of happening is the stuff in the brackets is getting passed to the quasi-quoter and turned into Haskell. So we kind of allow you to use concrete syntax, whatever concrete syntax you like, to generate Haskell terms. Of course, we also want to splice in computed subterms, which is what we're doing here. So that's an anti-quote. It's kind of the Lispy term would be anti-quotes. The template Haskell term would be splice. The kind of meta-ML, meta-OCaml term would be escape. And this lets you do the kind of splicing together that I was talking about. So as you construct these terms, you have these term with holes, plug some more terms in, build larger terms, and eventually you're going to get some program out, some closed term that you want to run. So again, this is just syntactic sugar. Okay? So let me show you what this elaborates to. So here's what this function elaborates to. It's just a pile of constructor applications, right? So you could have written this by hand yourself, they're equivalent. But I'm going to argue the quasi-coding is a little bit nicer. Again, this is what this elaborates to. So you can use combinators to do this, probably. But quasi-coding is a little bit nicer because it lets you, I haven't shown you here, but it will let you actually pattern match on values. So that's an advantage. It also provides location information here. So if you have an error in your generated code, you can trace it back to the point in your Haskell program where that term is generated. It's not type correct, but at least it produces kind of syntactically correct terms because you're using a data type here. So now I'll move to a slightly larger example. So this is a DFA compiler. It's part of a regular expression compiler. And here our goal, just bear with me, or humor me, the goal here is to do runtime code generation. So at runtime, I'm going to get some regular expression, and I want to compile it to a regular expression matcher. So I want to compile to a function I can actually call. So this really has to be type safe. We're going to walk through this, and this is kind of GHC versions. You could write this. But I want to talk about how to think about this and how you might modify or generate a type system for this kind of language that would let you preserve type safety. Okay, so to point out the type signature, they're not very useful. They're not very informative. Certainly, they're not useful for type correctness because what are we doing? We're generating a C function, but it's just a C function. The type there doesn't say anything about the type of the C function itself. It's just abstract syntax for a C function. Not particularly helpful. Similarly, we're generating C statements, but it doesn't really tell us anything informative. Okay, so let's look at this anti-quoting, how it may affect our type system. So, okay, here we're just splicing in some integers, and notice the syntax is slightly different. You can think of it as kind of type annotation, saying we're splicing in integers. Okay. But this is more interesting, so we have an anti-quote. So we're actually splicing in a bunch of statements that are being computed somewhere else. But we don't know, for example, what free variables those statements are going to use. This might be a challenge for our type system. So let's look at who generates the function that actually generates these statements here. Okay, it's getting generated by this state to C, and of course, what does state to C do? Well, it's also generating some more statements and splicing them and calling this other function. And what does this final function do? Well, it actually has some free variables that seem to refer back to the original top-level guy in the call graph. So if we're designing a type system, we need to track all this stuff. It's not really obvious how this is going to work, right? So let me kind of get to the punchline here. Right? So here's the GHC version. I'm going to show you the MetaHaskell version here. So notice the change here on the function type. We actually get a fun pointer back. It says this is actually a C function pointer, and it has the correct type that we expect our function to have when we write it. So it's actually a function from string to int. So to tell us when we pass it a string whether or not it matches our regular expression. Similarly, the type signature on the other two functions that are generating statements have changed, and they've captured the details necessary to ensure that this is type. So I want to emphasize that, so this actually runs. You can download MetaHaskell. You can use this kind of cut-down version of C as an object language. And although I've annotated the functions here, these are inferred by the system. So these are actually annotations that are inferred by MetaHaskell. So let's look again at this kind of type system, kind of get an idea of what's going on. Okay, so as I said, we have some free variables here. Let's really syntactically obvious here what's going on. See some free variables. Okay, so they show up in a type. And how do you read this type? So this says that in an environment where except is an integer and state is an integer, and we may have some other stuff represented by the gamma, this guy has type void. So we're just really using row polymorphism here to capture the typing environment of this guy. Okay? But it's obvious that state and except must be in a type environment because they show up syntactically in this term, right? Well, what about state to C? Okay, well this S variable shows up syntactically again as a free variable, so we know that guy must appear in the environment. But because of the recursive call, because we're splicing in these statements that are being generated, except and state must also show up in the environment. So there's some sort of unification going on here, right? When we see that there's this subterm being constructed, we look at its type, do some sort of unification between these two gammas, and come up with a type for our top-level function here. So it's not quite so obvious that this is actually quite tricky. So how do you think about this? This anti-quotation really complicates things. So I kind of like to encourage you to think about things this way. So take your favorite functional programming language or programming language, and take the syntax-directed version of its type system. And of course, if you have a favorite language, surely it has a type system that has a syntax-derived formulation, right? Syntax-directed formulation. So you have these terms and these derivations. So how does anti-quotation kind of change our view of the world? Well, now we have terms with holes. This is where the kind of syntax-directed part comes in. But we also have these typing derivations with holes. We have these kind of partial typing derivations. So we need to capture this partiality in the type system and pair these partial terms with their partial derivations. When we do the splicing, this anti-quotation, splicing things together, we need to somehow introduce ways of capturing the constraints between these things. So how are you going to do this? Well, you're going to do this with type variables. So we've modified the type system here. So this gamma is a type variable that helps us capture the constraints that arises from merging these two subderivations together into building this larger term. So we're splicing in these statements as a subterm. So we have to merge together the information about that derivation, hook it up with the derivation of the term in which it's being inserted. So there are a lot more details in the paper about this. I have described the properties we want from the metaprogramming system in the paper. I haven't gone into it here. There's a type system for an idealized meta language. So I made a conscious decision to not show any typing rules here. I don't know if that's correct or not, but I was experimenting. Let me know if it was a miserable failure. So there is a type system for an idealized meta language that sort of captures the notion of what MetaHaskell is doing. There are two object languages, kind of a core mini ML. And then you might think, does this stuff really generalize, or kind of piecing together these type environments using row variables to capture them? So what about a substructural language, a linear language? Well, it turns out that it works there too, and you can actually get inference. So I've done linear ML. There's an example in the paper of a type system for linear ML, a linear language you can embed this way. You can still write open terms. You can use anti-quotation, and so you still get inference. It still all works out. There's also more details of this C-like object language description of the implementation. And again, this is something you can download. So all three of these object languages work, and you can download them and run them. And there's again, when engineering this stuff, the question is, do you have to really add a lot of code to the implementations for each new object language? And the answer is no. It turns out there's only about 10 to 20 lines of code you need to change. The really kind of fundamental trick here is capturing the constraints in these derivation trees that you're piecing together with new kinded object language type variables. And then you quantify over those object language type variables at the meta language level. I described that also in the paper. Of course, there's a huge amount of related work also described in the paper. So I'm ready to take questions.
Thank you very much.